The universe does not end in any direction you can point to. Even now, as you breathe gently in the dark, space is stretching silently around you, every second widening the distance between galaxies, carrying them farther and farther apart on a fabric with no clear edge. What we call the edge of the universe is not a wall or a border. It's a question, a horizon shaped by time, motion, and the speed of light, a boundary that moves as the cosmos expands. And tonight, we will drift toward that quiet frontier. If this calm journey brings you peace or helps you fall asleep to the sound of the cosmos, your gentle like or soft tap on subscribe means more than you know. Thank you for being here in this quiet corner of the universe. Now, we drift into part 1. Part 1. What do scientists mean by the edge of the universe? There is no physical boundary floating in space, no cosmic fence where everything simply stops. Instead, the edge is a concept shaped by what light can show us. The universe has a visible horizon, a distance beyond which light has not had enough time to reach us since the Big Bang. As you listen, that horizon expands, not because we are moving toward it, but because spacetime itself is stretching quietly between every galaxy. To understand that idea, imagine standing on a shoreline at night, looking toward an ocean whose opposite shore you will never see. Not because it isn't there, but because the world is too large and the night too dark. The sea stretches beyond your sight, yet you know it continues. That is what the edge of the universe is like. A limit shaped not by the universe ending, but by our ability to see within it. A horizon made of time. Even now, as you breathe gently, the light from the farthest galaxies is still on its way toward you, traveling across distances so vast that the numbers lose meaning. That light has spent billions of years crossing the expanding fabric of spacetime. And because the universe has a beginning, a moment when light could first travel, there is a maximum distance from which any photon can reach us. Everything beyond that is not hidden behind a wall. It is simply too far away for its light to have arrived yet. This distance is called the observable universe. It forms a sphere around us, about 46 billion light years in every direction. Not 13.8 billion, even though the universe is that old, because space itself has stretched over billions of years, carrying galaxies farther from us even as their ancient light travels toward us. It is one of the quiet wonders of cosmology. The farther we look, the more space we find. The phrase edge of the universe can be misunderstood because it sounds like a boundary you could reach if you had enough time or speed. But nothing in the cosmos behaves that simply. What we see is defined by how long light has been traveling, not by where the universe ends. There is no sign that the universe ends anywhere. There are no indications that the cosmic fabric has borders, no physical edges where stars fall off or galaxies stop forming. In every direction astronomers look, space continues smoothly, the same structures repeating on enormous scales, clusters, filaments, voids, and more clusters drifting beyond them. The true edge, then, is a horizon, a limit created by light itself. When the universe was young, just a few 100,000 years after the Big Bang, it was too hot for atoms to form. Photons bounced wildly off charged particles, unable to travel in straight lines. Space was opaque, glowing, and dense. Only when the universe cooled enough for electrons to settle into atoms did light break free and move unhindered. That first light now fills the entire sky as the cosmic microwave background, a faint microwave glow detected by satellites like COBE, WMAP, and Planck. This ancient light forms one of our deepest boundaries. It is the farthest back in time we can see. No telescope can look past that moment because the universe before it was fogged with plasma. It is a natural barrier, not a wall, but a veil. Beyond that veil, the universe continues. It may contain regions unimaginably distant, entire clusters of galaxies whose light will never reach us, even if we wait forever. Those regions are not part of the observable universe, but they are part of the universe. What makes this horizon feel like an edge is the accelerating expansion driven by dark energy. For reasons still only partly understood, The universe is not only expanding, it is expanding faster and faster. The space between distant galaxies stretches more quickly than it did billions of years ago. This means that some galaxies are receding from us faster than the speed of light, not because they are moving through space at that speed, but because space itself is expanding. Einstein's relativity allows this. Objects cannot move through space faster than light, but space can expand at any rate. This creates another boundary, the cosmic event horizon, a region beyond which events can never influence us because the expansion of the universe carries them away faster than light can bridge the gap. Even if a distant civilization sent out a beam of light aimed directly at us today, some of those beams would never arrive. The universe expands too swiftly for their light to catch up. That horizon is not the same as the distance light has traveled since the Big Bang. It is a deeper limit, one that tells us what parts of the cosmos will remain forever out of reach, even in the far future. So what do scientists really mean when they talk about the edge of the universe? They mean these horizons, surfaces of knowledge defined not by physical structures, but by the laws of spacetime. They mean the boundary created by the age of the universe and the boundary created by its expansion. They mean the limit to what can ever be observed or understood from our location in space and time. But these horizons are not fixed. With every second that passes, the observable universe grows larger. Light from new regions reaches us, revealing galaxies that were once beyond our view. At the same time, other regions slip beyond our event horizon, carried away by accelerating expansion. The cosmos is a moving stage. The parts we can see and the parts we can never see shift quietly with every moment. This leads to a deep and gentle truth. The edge of the universe is not a place, it is a time, a moving frontier shaped by the finite speed of light and the evolving fabric of spacetime. Imagine this. If the universe somehow stopped expanding and we waited long enough, we would eventually see everything that exists, every galaxy that ever formed. But because expansion accelerates, the opposite is true. The longer the universe continues, the less of it we will ever be able to reach. The knowable world shrinks as the universe grows. This is the cosmic boundary paradox. The horizon expands outward, but the portion of the universe that can ever affect us retreats inward. The universe grows larger, yet the region we can interact with becomes smaller. And still, none of these limits represent an edge in the ordinary sense. There is no cliff at the end of spacetime, no cosmic dome, no outer surface to touch. If you were to drift in a spacecraft toward the farthest galaxy we can currently see, nothing unusual would happen as you approach the edge of the observable universe. You would not cross a line or feel a shift. You would simply travel deeper into space while the Earth receded behind you. The light reaching your eyes would change, becoming older and more stretched by expansion, but there would be no sign that you were approaching a boundary. The edge is something you only perceive from where you stand. Every observer, no matter their location in the universe, sees themselves at the center of their own observable sphere. Every galaxy has its own horizon. Every point in spacetime carries its own bubble of visibility. The edge is always personal, always relative, always defined by light's long journey through the darkness, and that is what makes it so beautiful. The edge of the universe is not a barrier that limits the cosmos. It is a reflection of where we stand inside it, a reminder that even in the vastness of everything, our perspective is just one small window into a much greater whole. And as we continue this quiet journey, one question naturally follows. Part 2. Why the observable universe isn't the whole universe. If you could drift outward forever, past stars, past galaxies, past the glow of ancient light, you would eventually reach a region where nothing has ever had time to reach us, not even a single photon. This boundary is called the cosmic light horizon. Beyond it, the universe continues, but it remains hidden, like a landscape behind a moving curtain. To understand this horizon, imagine standing in a dark field at night with a lantern. The light you cast extends outward in a widening sphere, illuminating more and more of the landscape around you. But beyond a certain distance, the light simply hasn't reached yet. The landscape is still there, quiet, real, full of detail, but invisible because photons have not arrived to reveal it. Our view of the universe works the same way. The Big Bang was the moment the cosmic lantern was lit, and the sphere of light it has produced forms the limit of what we can see. This boundary does not mark the end of space, it marks the limit of time. The observable universe is defined by the age of the cosmos, about 13.8 billion years. Light moves at a finite speed, so the farthest objects we can see are those whose photons have had enough time to reach us across an expanding cosmos. Because space has been stretching for billions of years, those regions are now roughly 46 billion light-years away. Anything beyond that lies outside our observable bubble, but not outside the universe itself. The mistake people often make is imagining the observable universe as a physical shape embedded in some larger void. But it is not an object floating inside a bigger one. It is a perspective, a window shaped by time. If you move to another galaxy entirely, even one unimaginably distant, your observable universe would shift with you. You would stand at the center of a new cosmic sphere, with new galaxies entering your field of view and others slipping away. The universe does not have one observable boundary. It has countless ones, one for every observer in existence. This is one of the most humbling truths in cosmology. Our picture of the universe is not absolute. It is conditional, built from the limited light that has reached us. When we talk about the size of the universe, what we are actually describing is the radius of the light we have received so far. The universe itself may be far larger, perhaps infinite, while our visibility is limited to a small, though enormous sphere carved out by the speed of light and the age of time. When astronomers gaze outward with telescopes like Hubble or James Webb, they are not seeing the universe as it is now, but as it was at different stages in its history. The farther they look, the deeper into time they peer. At 10 million light-years, they see galaxies as they were 10 million years ago. At 10 billion light-years, they see them as they were near the dawn of galaxy formation. And when they look nearly 13.5 billion light-years away, they approach the faint afterglow of the Big Bang, the cosmic microwave background. But beyond this ancient glow is more universe, vast regions we can never see because their light has not yet had time to arrive, and perhaps never will. These regions are not hypothetical. They almost certainly exist. They must exist, mathematically and physically, because nothing about the universe indicates a boundary. Wherever we look, galaxies appear distributed evenly on the largest scales. Space does not thin out or fade to black. Structure simply continues, repeating patterns of clusters and voids over and over again. Yet our ability to witness that continuation is temporary and fragile. The accelerating expansion of the universe, driven by dark energy, ensures that some galaxies will remain forever beyond our reach. Even if we waited trillions of years, even if we matched the speed of light and traveled outward in a ship, we would still never catch up to many distant regions. The fabric of spacetime stretches too quickly. Those galaxies recede faster than any signal, any ship, any beam of light could ever reach them. In a sense, the observable universe is shrinking, not in size, but in accessibility. As time moves forward, more and more galaxies cross beyond the cosmic event horizon, carried away by expansion faster than their light can ever return to us. They do not vanish, but they slip into permanent silence. Their stories continue in darkness, and yet for now, we see enough to understand a profound truth. The universe we observe is only a fragment of the whole, a small patch of a vastly larger reality. One way to picture this is to imagine drops of ink swirling in water. Near the center, the ink is dense and vibrant. Farther out, the color fades gradually. Not because there is less water beyond, but because the ink simply hasn't reached those regions yet. The observable universe is like that central swirl, the region tinted by the light that has had enough time to reach us. Everything beyond remains clear and unseen, though it is still part of the same ocean. Another way is to think about sound. Imagine a distant orchestra playing in the mountains. You're standing in a valley far away. The notes you hear are those that have had time to travel across the landscape. Some reach you clearly, others arrive faint and distorted, and many, especially the earliest ones, never reach you at all. They are still part of the performance, you are simply too far away to hear them. The universe works this way. We hear only the notes that have arrived so far. This leads to a remarkable realization. The universe may be infinitely larger than the region we can see. It may contain structures that dwarf our observable volume, superclusters stretching beyond any scale we have ever imagined. There could be galaxies far older than any we can detect, whose light has been forever isolated by expansion. There could be physics playing out beyond our horizon that differs subtly from the physics we know, not because the laws are different, but because the conditions have evolved in ways we cannot witness. And yet, even if the universe is infinite, our observable universe will always be local. It is the universe as filtered through our particular position in space and time. Another observer, living in a galaxy 20 billion light-years away, if such a location could be meaningfully defined within the expanding fabric, would see a completely different patch of sky. Their cosmic horizon would contain galaxies we will never see. Their edge would be shaped by a different history of light. This relativity of perspective is not a poetic notion. It is built into the equations of general relativity. There is no universal center, no single favored viewpoint. The universe has no edge in space, only edges in time carved by the finite reach of light. So why isn't the observable universe the whole universe? Because the universe is older, larger, and more intricate than the light that has arrived so far. Because the cosmos is not limited by our ability to witness it. Because time has not passed long enough for us to see the entire picture. Standing on a quiet planet, on a quiet night, we look outward through a narrow window. It widens slowly with each passing moment, letting more ancient light slip inside. But the world beyond that window is vast, boundless, forever unfolding. And as we continue drifting through this calm story, one question gently rises. Part 3. What lies beyond the cosmic light horizon? Scientists believe that space beyond our horizon likely looks much like the region we inhabit, filled with galaxies, dark matter, and cosmic structure. But we cannot see it because the expansion of space has carried those regions away faster than light can cross the growing distance. Out there, the universe continues quietly, perhaps endlessly, but forever unobservable from our point in spacetime. To imagine this realm, you must picture a universe that does not end where our visibility fades. Instead, think of the horizon as a soft boundary painted by the age of light, not the edge of reality itself. Just as a traveler at sea sees only the curved line of the Earth and not the continents beyond, our cosmic horizon hides vast regions that unfold in every direction. Those regions remain unlit in our sky, not because they are empty, but because their photons have never had time to reach us. This idea alone reshapes how we think about existence. The stars you see above you, the galaxies imaged by Hubble and James Webb, and the structures mapped by cosmic surveys, all of them form only a small portion of what's truly out there. The observable universe is a bubble of knowledge expanding through darkness. Outside that bubble lies a cosmic ocean whose waves of light have yet to arrive. So what lies in that unseen expanse? The simplest and most supported answer is more of the same. More galaxies drifting in clusters, more dark matter sculpting invisible frameworks, more filaments stretching across unimaginable distances, more cosmic voids where matter is sparse and silence reigns. Nature seems to repeat its structure across scales, and surveys of the universe show a kind of statistical uniformity. The same patterns appear in every direction and at every depth we can observe. If the universe looks this way everywhere we've been able to measure, the safest assumption is that it looks similar in regions we cannot. Still, similar does not mean identical. The further we travel in thought, the more time becomes a factor. Light from distant regions not only originates from far away, it originates from the deep past. When you see a galaxy 10 billion light-years away, you are seeing it as it was 10 billion years ago. As you extend this thought outward, you soon realize that galaxies beyond the cosmic light horizon exist in their own present moment, one we will never witness. You will never see how they evolved, never see their stars form or die. Those stories remain beyond the reach of every telescope ever built and every telescope we could ever imagine. The universe beyond the horizon is unobservable, not because it is unknowable, but because the expansion of space has outpaced our ability to receive its light, and the expansion is accelerating. That means each second, more and more of the universe slips beyond the event horizon, quietly removed from our cosmic future. The distant galaxies continue on their own paths, untouched by us, unreachable forever. But though we cannot see them, scientists can still infer what they are like. The evidence lies in the cosmic microwave background, the faint glow left over from the early universe. Its temperature variations reveal that the cosmos was almost perfectly uniform when it was young. Tiny fluctuations in density, the seeds of future galaxies, were spread evenly across immense distances. This uniformity implies that the regions beyond our horizon were formed from the same primordial blueprint as the regions we observe. Those distant galaxies began with the same ingredients, governed by the same physics, shaped by the same cosmic forces. If you could drift far enough beyond our visible bubble, you would likely find galaxies swirling in familiar spirals. You would find clusters bound by gravity. You would find dark matter halos, silently sculpting star formation. You might even find life, though that question remains open, suspended between hope and humility. Of course, some scientists wonder whether the universe may contain gentle variations beyond our horizon. Not dramatic differences like alternate laws of physics. There's no evidence for that. But subtle shifts in the distribution of matter or the timing of cosmic evolution. Inflation theory predicts that the universe is vastly larger than the part we see, and that different distant patches may show small differences in structure. The variations would be slight, almost invisible, stretched by inflation into smoothness. But these questions are delicate whispers at the frontier of cosmology. The universe beyond our horizon cannot send us answers. We can only reason from the clues left behind. There is another idea, more philosophical than empirical, yet grounded in the logic of cosmology. The unseen universe might be infinite. It might extend without end in all directions, containing more galaxies than any number we could write. If this is true, then everything we know, every star, every cluster, every filament of matter, is just one island in an endless archipelago of cosmic landscapes. And there is a quiet beauty in this thought, because it means that even now, the universe is not something that fits into a finite picture. It is something that extends beyond imagination, beyond our senses, beyond our comprehension, something that will always be larger than we can know. In this way, the cosmic light horizon becomes a reminder of humility. It tells us that our knowledge is partial, that the universe is not defined by our perspective, and that reality stretches far beyond the boundaries of our understanding. But if the universe beyond our horizon likely resembles the universe we see, why can't we access it? The answer lies in the interplay between distance and expansion. Imagine placing dots on a balloon and gently inflating it. The dots do not move across the surface expands between them. Similarly, galaxies are mostly stationary relative to their local regions. It is space itself that stretches. At great enough distances, the stretching happens faster than light can cross the growing gap. This does not break any laws of physics. Light still moves locally at the speed of light, but space is not constrained by that rule. It can expand at any rate. This expansion creates a horizon that no object can cross. Even if you traveled at the speed of light toward the edge, the space between you and that boundary would expand even faster, like a tide running ahead of you. The horizon is not a wall. It is a moving frontier, always receding. And so the universe remains divided into two types of regions, the regions we can observe and the regions we cannot. Yet both are equally real. The unobservable universe is not less significant. It is simply farther. It continues to evolve in silence, Stars there burn, collapse, and seed new generations. Galaxies merge and drift apart. Dark matter sculpts new structures. The cosmic web stretches, reshapes, and flows. Entire histories unfold, parallel to ours but forever beyond our reach. This realization is not sad, it is deeply peaceful, because it means the universe is not empty beyond our sight. It is full, alive with motion, vibrant with structure. Cosmologists often say that we live in a universe too large for any one observer to know. And this, quietly, is part of its beauty. The cosmos does not shrink to match our perspective. It remains vast, it remains mysterious, it remains more than we can ever hold in our minds. When we look out into the night sky, we see only a fraction of what exists, yet that fraction tells us enough to infer the larger whole. What lies beyond the cosmic light horizon is not a void or a boundary. It is the continuation of everything we already see, stretching endlessly into the dark. And as we drift deeper into this quiet story, another question naturally rises. Part 4. Why the universe expands. Faster the farther we look, distant galaxies appear to race away from us at extreme speeds, not because they are moving through space, but because space itself is expanding. The farther away an object is, the faster the fabric stretches between us and it. At great enough distances, this stretching exceeds even the speed of light, a phenomenon allowed by relativity. And that creates an apparent edge, one that isn't fixed, but flows outward like a tide. To understand this strange behavior, imagine drawing dots on a balloon. If you slowly inflate the balloon, the dots appear to move apart, though none of them slide across the surface. Their separation increases because the surface itself expands. The universe behaves the same way. Galaxies are not rushing through the cosmos like particles fired from a cannon. Instead, they are mostly stationary relative to the space around them. It is the space between them that grows, carrying them farther apart. This idea was first suggested in the early 20th century by astronomers studying the light from distant galaxies. They noticed something subtle but universal. The farther away a galaxy was, the more its light was stretched toward the red end of the spectrum. This redshift was a clue, a fingerprint of motion written into the wavelengths themselves. In 1929, Edwin Hubble revealed the truth. The universe was expanding. The galaxies weren't just drifting, they were embedded in a stretching fabric. From that moment on, our picture of the cosmos changed forever. Instead of a static, eternal universe, we found ourselves living inside a dynamic one, a universe that grows, breathes, and evolves. The key to this cosmic behavior is a simple relationship called Hubble's law. It states that a galaxy's apparent speed away from us is proportional to its distance. Double the distance, double the apparent speed. This is why the expansion becomes so astonishing at large scales. A galaxy a billion light-years away recedes slowly. One 10 billion light-years away recedes much faster. And one at the edge of the observable universe may recede faster than light itself. This does not break Einstein's rules. Relativity forbids objects from moving through space faster than light, but it places no speed limit on the expansion of space. Space is not a substance that moves. It is a geometric framework that can stretch freely. The speed limit applies only to local motion, not to the changing distance between far-flung galaxies. This is why, as you move your gaze deeper into the cosmos, the recession speeds rise. The expansion accumulates, adding more and more stretch between us and the distant regions. At great enough scales, the expansion overtakes the ability of light to cross the growing gap. These regions become unreachable, forever carried away by the flow of spacetime. That is what creates the sense of an edge, not a boundary carved in stone, but a boundary created by speed, a flowing limit, a horizon of motion. The universe's expansion is not static. It does not unfold at a constant rate. In fact, about 5 billion years ago, something remarkable happened. The expansion, which had been slowing due to gravity, began to accelerate. This shift was so subtle, so slow, that it wasn't noticed until the late 1990s, when astronomers studying distant supernovae made an unexpected discovery. Instead of slowing down, the universe was speeding up. The cause of this acceleration remains one of the great mysteries of modern physics. We call the driving force as dark energy, a name that describes our ignorance more than our understanding. Dark energy appears to be a property of space itself, a kind of outward pressure that grows as space-time expands. Unlike matter, which dilutes as the universe grows, dark energy seems constant per unit volume. As the universe stretches, more of it comes into existence, amplifying its own effect. This sets up a cosmic tension. Gravity pulls inward, trying to slow the expansion. Dark energy pushes outward, accelerating it. At the largest scales, dark energy wins. As a result, regions of the universe are receding from us faster than light, not because they move quickly, but because there is simply more space between us than light can bridge. Every second, more galaxies slip across that horizon, carried away by a tide that never rests. This is why the universe expands faster the farther we look, not because distant regions are different, but because the measure of expansion cumulates over distance. Space does not stretch evenly. It stretches proportionally. 1 meter expands by a tiny amount. 1 billion meters expand by 1 billion times that amount. At cosmic scales, these small stretches add up to staggering speeds. This also leads to a quietly profound truth. There are galaxies whose light will never reach us. Not now, not ever. They are not hidden behind dust or blocked by matter. They are simply too far away in an accelerating universe. Their photons, even if fired straight at us, are overtaken by the growing expansion. Space outruns them. Those galaxies vanish beyond what astronomers call the cosmic event horizon. This horizon is not the same as the light horizon. The light horizon shows us the farthest objects that have already sent light to us. The event horizon shows us the farthest objects that can ever send light to us in the future. Anything beyond that boundary cannot influence us in any way. It is a one-way veil, a limit of causality, a consequence of acceleration. Still, beyond that horizon, the universe continues its quiet rhythm. Galaxies there form stars and lose them. Worlds orbit suns we will never see. Clusters collide in silent gravitational dances. Their stories unfold parallel to ours, but forever disconnected by the growth of space. The expansion of the universe also shapes the way structures form. In the early universe, matter was dense, and gravity could pull galaxies together easily. But as the expansion accelerated, gravity found itself working against an ever stronger cosmic tide. Structures grew more slowly, galaxies became isolated, voids expanded. The cosmic web, once tightly woven, became stretched across greater distances. In the distant future, tens of billions of years from now, the expansion will isolate every galaxy outside our local group. The sky will grow emptier. Beyond Andromeda and a few satellites, all other galaxies will fade beyond the horizon. The cosmos will look lonely, though it will remain vast. Yet none of this means the universe is running away from us. Every point in the universe experiences the same phenomenon. If you move to a distant galaxy, you would see the same pattern. Galaxies farther from you would recede faster. The expansion is symmetric. There is no cosmic center, no privileged location. Every observer sits at the heart of their own expanding sphere. This idea is one of the great harmonies of cosmology. The universe stretches uniformly from every point. Every location participates in the same cosmic motion. Every galaxy is both still and drifting. The expansion does not fling us outward. It carries us gently. We are not moving through space at unimaginable speeds. We are floating through the growth of space-time itself. And the farther we look, the more of that growth we witness. The faster the recession speeds become, the more the universe reveals its accelerating nature. There is a quiet comfort in this. The universe does not expand into emptiness. It expands into itself. Space creates more space. Time unfolds more time. The cosmos is not moving away from us. It is blossoming around us like an infinite flower whose petals open gently in every direction. And as we drift deeper into this expanding picture, one question naturally follows. Part 5. What is the cosmic microwave background, and why is it a boundary? The oldest light we can see surrounds us as a faint microwave glow, the cosmic microwave background. It marks the moment when the universe first became transparent, around 380,000 years after the Big Bang. Beyond that moment, light could not travel freely, so this ancient surface becomes another kind of edge, not the edge of the universe, but the oldest visible chapter of its story. To understand this boundary, you must imagine a universe very different from the one we inhabit now. Not a cosmos filled with galaxies and stars, but a hot, dense ocean of particles. In those early moments, the universe was so energetic that atoms couldn't exist. Electrons and protons drifted freely, and photons, particles of light, bounced constantly between them like a storm of sparks trapped in fog. In this early plasma, light could not move in straight lines. Every photon was scattered almost instantly, repeatedly colliding with charged particles and changing direction. This made the universe opaque, glowing from within but impossible to see through. The cosmos was, in a sense, lit from the inside, but without transparency. No object could cast a shadow, no light could escape over long distances. It was a world of brightness without vision. Then, something remarkable happened. As the universe expanded, it cooled. Temperature fell from unimaginable trillion-degree heat toward a threshold where electrons could finally settle into stable orbits around protons. These newly formed atoms were electrically neutral. They no longer scattered light the way free electrons did. Suddenly, photons were freed. Light could travel in straight lines for the first time. This moment is called recombination, and the instant light began, its uninterrupted journey is called last scattering. The photons released then have been traveling across the universe ever since, stretched by cosmic expansion into microwaves. They now fill the entire sky, forming the cosmic microwave background, an ancient surface of light surrounding us like a spherical fossil. This surface is the oldest picture we can ever take of the universe, not because our telescopes are weak, but because the universe itself does not allow us to see earlier. Before recombination, the cosmos was opaque. Light simply could not travel freely. So when we point telescopes as far back as possible, what we see is not the Big Bang itself, but the fading glow from when the universe first became clear. The cosmic microwave background, or CMB, is a boundary of knowledge, not a physical wall, but a surface formed by the limits of physics. It is the earliest accessible moment in the universe's visible history. And yet, this ancient light is not uniform. It is gently patterned. Satellites like COBE, WMAP, and Planck have mapped it with exquisite precision, revealing fluctuations in temperature as small as 1 part in 100,000. These subtle variations are not noise. They are the seeds of everything. Regions just slightly denser than others eventually grew into galaxies, stars, planets, and the structures that fill the universe today. When you look at a map of the CMB, you're not just seeing light, you're seeing the blueprint of existence. Every ripple in the pattern corresponds to a tiny difference in density. Some regions contained slightly more matter, others slightly less. Over billions of years, gravity amplified these differences. Dense regions became galaxies and clusters. Sparse ones became cosmic voids. The modern universe, the vast cosmic web stretching across space, comes from these tiny temperature ripples frozen into the CMB. This is why the cosmic microwave background is so important. It is a snapshot of the universe in its infancy. It contains clues about the universe's age, shape, composition, and fate. It tells us about inflation, the brief exponential expansion that occurred in the earliest moments. It reveals the presence of dark matter and dark energy through the way sound waves ripple across the primordial plasma. It even hints at the geometry of spacetime itself. The CMB is not simply a boundary, it is a message, a whisper from a younger universe. But what does it mean to call it a boundary? It is a boundary in time, not in space. The CMB forms a spherical shell around us at a distance of about 46 billion light years. But its significance lies in its age, not its position. When we observe the CMB, we are looking back 13.8 billion years, almost to the beginning. Before that moment, no light could travel far enough to reach us, so the CMB marks the limit of what we can see using electromagnetic radiation. You can imagine it like the ocean surface frozen in place. Below it lies a different world, one we cannot photograph. We know it existed. We can derive what happened from physics, but its details remain veiled because the universe has no older light to show us. Beyond that boundary lies the first 380,000 years of cosmic history, a period we must understand not through direct observation, but through theory and indirect signatures. That early epoch includes the inflationary period, where space expanded faster than any speed the universe normally allows. It includes the formation of quarks and gluons into protons and neutrons. It includes the earliest interactions between gravity and quantum fields. Yet all of that remains invisible because light could not travel freely until recombination. The CMB is therefore a horizon, not a horizon in space, but in visibility. Another remarkable aspect of the CMB is how uniform it is. Despite spanning the entire sky, the temperature varies by only a tiny amount. This tells us that the early universe was astonishingly smooth. Smooth enough that regions separated by huge distances must have once been in close contact. This is one of the strongest pieces of evidence for cosmic inflation, a period when the universe expanded from subatomic scales to macroscopic ones in a fraction of a second. Inflation explains why the CMB looks so similar in every direction. Without it, regions of the sky would not have had enough time to equalize their temperatures. When we look at the CMB, we are observing the stretched-out echo of that early inflationary burst. It is a whisper from the beginning woven into the microwave sky. And though the CMB is ancient, it is incredibly faint. Its temperature is just 2.725 degrees above absolute zero. In fact, if your microwave oven weren't shielded, it would be able to detect the CMB. The glow is everywhere, in every direction at all times, day or night. It wraps around the Earth, surrounds every galaxy, and fills all of space. It is the oldest light in existence, washing gently over the universe. But even as we marvel at it, the CMB reminds us of a deeper truth. The universe had a beginning. Its existence is the closest visual evidence we have of that moment. It is the cosmic dawn preserved as light. And the fact that it forms a boundary reveals something else. The universe does not let us see everything. There are limits, not because the cosmos hides things, but because physics has rules. Transparency has a starting point. Before that, the universe was too dense, too hot, too chaotic for light to carry information across space. So the CMB is a reminder of both knowledge and confinement. It shows us the earliest chapter we can see and marks the chapters that remain forever unreadable through light. Yet beyond that boundary, the universe is far from empty. It is simply invisible. The early moments of cosmic evolution continue behind the curtain, written in the equations of physics and the geometry of spacetime. This ancient glow forms one of the most poetic limits in all of science, a boundary not of space, but of memory, the oldest picture the universe will ever give us. And as we drift from this chapter into the next, another quiet question begins to rise. Part 6. Why the universe has no center and no outside. If the universe is expanding, it is natural to wonder where it is expanding from. But there is no center and no edge. Every point in the universe, including the one where you are lying now, is moving away from every other point in a cosmic pattern without a privileged center. Expansion is not an explosion into empty space. It is space itself enlarging everywhere at once. This idea can feel counterintuitive because our daily experiences teach us the opposite. When something expands, like a ripple in water, or the steam from a kettle, or the shock wave of an explosion, there is always a location where the motion began, a center, a starting point, a place you could point to and say, it started there. But the universe does not behave like the world we know. Its expansion is not like an explosion spreading out from a point. It is more like the stretching of a fabric, or the inflation of a balloon, or the widening of a horizon that has no edges attached to it. Space does not expand from somewhere. It expands everywhere. To get a sense of this, imagine again the balloon analogy. but think carefully about what it represents. If you draw dots on the surface of a balloon and then inflate it, each dot moves away from the others as the surface grows. But from the perspective of any single dot, the situation appears identical. All the other dots recede, and none of them appears to hold a central position. The expansion has no center on the surface of the balloon. In this analogy, the two-dimensional surface of the balloon is like our three-dimensional universe, and the air inside the balloon is not anything real. It represents mathematical space outside our universe, not physical space. In reality, there is no outside. The universe is not growing into something, it is becoming more of itself. This is one of the deepest lessons of modern cosmology. The universe does not require an external container. It creates its own space. It evolves within its own geometry. The moment you imagine the universe expanding into something else, you have stepped outside what physics describes. The fabric of spacetime is all there is. Outside of that fabric, there is no direction, no dimension, no emptiness to expand into, not a void, not a background, not a space waiting to be filled, just nothing, no stage at all. Expansion simply means that the distance between points increases. That's it. No external motion, no from and no into. This is beautifully captured in Einstein's general theory of relativity. Space is not a static arena, it is a dynamic, flexible, evolving entity. Gravity doesn't act within space. Gravity is the shape of space. And when the universe expands, it is the geometry itself stretching. This is why every observer, no matter where they stand, sees the same pattern. Galaxies farther away receding faster, stars drifting with the growth of space, the fabric stretching gently in all directions. No one stands at the center, and no one stands at the edge, because there is no center and no edge. The Big Bang does not describe an explosion in space, it describes the origin of space. When cosmologists talk about the universe beginning in a hot, dense state, they do not mean that all the matter once existed in a tiny spot inside a larger emptiness. They mean that the entire universe, the whole of space-time, was once compact, hotter, and denser everywhere, not at a single location, but at every location simultaneously. Every point in today's universe was once part of that early state. Every region was involved in the unfolding of space. Every galaxy traces its origin back to that same primordial moment. This is why the concept of a center makes no sense. The universe did not start expanding from one point. It began expanding as one point, and that point was not located anywhere. It was everywhere because the universe was smaller than any meaningful notion of place. To help visualize this, imagine standing on a vast sheet of rubber that stretches infinitely in every direction. If the entire sheet begins to expand, your position does not matter. Every point moves away from every other point. If you looked around, you would see the same expansion pattern everywhere. It would feel as if you were at the center of something, but so would every other observer anywhere else on the sheet. In the real universe, this expansion happens in 3 dimensions, not 2. And unlike the rubber sheet, it is not expanding on a surface in a higher dimension, it is expanding within itself. The next question that naturally arises is, if there is no center, then why do we seem to be at the center of our observable universe? The answer lies in the speed of light. We can only see as far as light has had time to travel since the universe began. This forms a visible sphere around us, the observable universe. But this sphere is centered on us only because we are the observers. Anyone else, living anywhere else in the cosmos, would see their own sphere of visibility centered around them. Every observer sees themselves at the center of their observable universe. This is not a privilege. It is a geometric consequence of perception. It is the same reason everyone standing under a sky sees the rainbow centered around themselves. The rainbow is not out there in a fixed position. It is built from the path light takes to their eyes. Likewise, the observable universe is shaped by the path light takes to reach us. We are not at the center of the cosmos. We are at the center of our cosmic horizon. And so is every distant galaxy. This symmetry is called homogeneity and isotropy. the assumption that the universe is roughly the same everywhere and in every direction. Observations heavily support this idea. Large-scale surveys show that galaxies spread out evenly across space, not clustering in one direction more than another. The cosmic microwave background looks nearly identical no matter where we point our telescopes. And the distribution of cosmic structures forms a pattern with no special center. These observations have led to what cosmologists call the cosmological principle. It states that on large enough scales, the universe is uniform. No special places, no cosmic center, no cosmic edge. It is a deeply humbling idea. The universe does not revolve around us or around anything. But this principle also protects us from strange alternatives. If the universe had a center, the expansion pattern would look different depending on where you stood. Some directions would show greater motion, others less. The cosmic microwave background would reveal asymmetries. Galaxies would cluster unevenly. We see no such patterns. Instead, we see uniformity. The universe expands equally everywhere. Space stretches no matter where you look, and this global expansion has no preferred origin. Another question often arises: if the universe has no outside, what caused the expansion in the first place? Here, cosmology becomes quiet, honest, humble. The equations describe how expansion evolves, not why it began. The cause of the Big Bang lies in a realm where physics approaches its limits. Some theories propose quantum fluctuations, others hint at eternal inflation, some speculate about higher dimensional origins, but none of these are proven. They remain possibilities, poetic and mathematical, not certainties. What is clear is this: the universe does not need an outside to expand. Expansion is not a motion into something, it is a change within space-time itself, a shifting of geometry, a gentle unfolding. In a way, the lack of a center is what makes the universe feel infinite. Not infinite in size, though that may be true, but infinite in perspective. No matter where you stand, the cosmos opens around you. Every location is the middle of its own story. Every vantage point reveals a different part of the whole. This makes the universe oddly intimate. We are not observers looking at something distant. We are participants inside a fabric that grows around us. And as we drift deeper into this vast, centerless cosmos, another quiet question begins to take shape. Part 7. How inflation created a boundary we cannot cross. In the first fraction of a second after the Big Bang, the universe expanded faster than any speed nature normally allows. This period, called inflation, stretched small quantum fluctuations into the seeds of galaxies and pushed distant regions beyond all possibility of communication. That ancient stretching created a permanent boundary, a horizon etched into the structure of space-time. To understand why inflation is so extraordinary, imagine trying to observe a cosmic event that lasts for less time than the blink of an eye. Far less, in fact. Inflation unfolded in less than a trillionth of a trillionth of a trillionth of a second. Yet, in that unimaginably brief sliver of time, the universe grew from subatomic scales to macroscopic ones. A region smaller than a proton expanded to something large enough to contain the seeds of everything we see today: galaxies, clusters, voids, and the cosmic web itself. This expansion did not break the cosmic speed limit because nothing moved through space faster than light. Instead, space itself expanded, and space is permitted to stretch at any speed, free from the constraints placed on objects moving within it. Einstein's relativity sets a limit on motion in space-time, not on the evolution of space-time itself. Inflation is the moment when the universe took advantage of this freedom. Before inflation, the cosmos was tiny, so small that every point within it was close enough to influence every other. Information could flow freely. Temperature, density, and energy could equalize. Everything had time to interact. Then, inflation hit. Space ballooned so rapidly that regions once tightly connected were thrust beyond each other's reach. The stretching was so dramatic, so absolute, that areas that were once neighbors became more distant than any signal could ever cross. Even if light had infinite time to travel, it would never reconnect those separated regions. inflation swelled the cosmic fabric faster than light could keep up, creating permanent causal islands. This is why we see such uniformity in the cosmic microwave background. Opposite sides of the sky have nearly identical temperatures and densities, even though they are too far apart to have communicated since the Big Bang. They were once neighbors before inflation expanded them apart. Inflation explains this otherwise impossible symmetry. The boundary inflation created is called the cosmic inflationary horizon. It is not a surface we can approach or touch. It is a relic of how fast space grew in the earliest moments. A horizon frozen in time, preserving the regions that inflation pushed beyond forever. Imagine painting tiny specks of dust on a balloon, then inflating it instantly by a factor of trillions. The specks would be separated so quickly that their arrangement would freeze. No matter how much additional expansion occurred later, those specks would remain beyond each other's influence. They would drift, yes, but their original distance would be locked in place by that first burst. Inflation created the same effect. Every region of space today carries a memory of that primordial stretching. The light we see from the cosmic microwave background is like the surface of a balloon representing the boundary of our observable universe. Beyond that surface lie regions that inflated away from us so swiftly that their light has never reached us. They remain there, silent and unreachable, not because they disappeared, but because spacetime forbids any communication between us. Inflation also magnified quantum fluctuations, tiny random variations in the energy field driving the expansion. These fluctuations were microscopic ripples, smaller than atoms, but inflation stretched them across cosmic distances, turning subatomic jitter into enormous structures. Where a fluctuation was slightly denser, gravity would later amplify it, forming galaxies and clusters. Where it was slightly thinner, cosmic voids emerged. In this way, the structure of the modern universe is the fossil imprint of quantum noise. Every star, every planet, every nebula, every galaxy cluster arises from those early seeds. Inflation is not just a process that occurred. It is a blueprint imprinted into the architecture of space. The permanent boundary that inflation created is not merely conceptual, it is measurable. The temperature fluctuations in the cosmic microwave background, mapped by Kobu, WMAP, and Planck, reveal statistical patterns that match exactly what inflation predicts. The scale of the fluctuations, the way they cluster, the ratios between hot and cold spots, every detail echoes the physics of inflation. These patterns allow scientists to estimate how fast inflation occurred, how long it lasted, and how it ended. They show that the seed fluctuations were nearly, but not perfectly, uniform, exactly the signature expected when quantum scales are stretched to cosmic proportions. But what's most striking is what this implies. We can only see a tiny fraction of the universe that inflation created. Because inflation expanded space so dramatically, the observable universe is just one small patch of a vastly larger whole. There are regions forever beyond our cosmic horizon, regions where inflation carried them out of reach before time even had a chance to begin flowing in a meaningful way. These unreachable regions are not alternative universes in a science fiction sense. They are simply parts of our universe that lie too far away for light or gravity or any signal to ever reconnect with us. Their existence is implied directly by inflation's speed and duration. If inflation lasted even slightly longer than expected, the universe could be effectively infinite, an enormous mosaic of regions like ours, each born from the same process but forever, isolated. If it lasted slightly less time, the universe could be finite, but still far larger than anything we can observe. Either way, the conclusion is the same. Inflation created a horizon we can never cross, not with rockets, not with light, not with time. The universe is stitched together in such a way that some parts are permanently out of contact with others. That boundary is not something we can travel toward. It is something built into the shape of reality. Another profound implication of inflation is that the universe appears incredibly flat, not curved like a sphere, nor saddle-shaped like a hyperbolic plane, but flat in the geometric sense. Inflation stretched space so drastically that any small curvature that might have existed became diluted. Like smoothing wrinkles in a sheet by pulling it taut, inflation flattened the cosmos. This flatness is measurable today. Observations of the cosmic microwave background show that parallel lines do not converge or diverge across cosmic distances. This is one of the strongest confirmations that inflation truly happened. Inflation also explains why the universe appears homogeneous, similar everywhere we look. Before inflation, the universe was small enough for temperatures to equalize. After inflation, that uniformity was preserved, even while distant regions flew apart faster than light. Without inflation, the universe would show wild temperature variations from place to place. Instead, the cosmic microwave background is astonishingly smooth. This smoothness is not an accident, it is a memory, a fossil from a time before inflation. Perhaps the most poetic aspect of inflation is that it hints at a universe with a past we cannot directly observe. The early cosmos was too dense for light to escape. Inflation pushed that opaque era beyond our horizon, forever removing it from view. The actual moment of the Big Bang, whatever its true nature, will never be visible. Not because of the limits of technology, but because inflation stretched the early universe beyond our observational reach permanently. In other words, inflation hides the beginning from us. What remains visible is its fingerprint, the cosmic microwave background, the distribution of galaxies, the emptiness of cosmic voids, the tiny lumps and bumps in the sky that whisper the story of quantum fluctuations expanded to astronomical scales. And yet, these clues tell us one thing with deep certainty. Inflation carved the limits of what we can know. Beyond those limits lies a vastness we can infer but never witness, a cosmic landscape stitched together by a burst of expansion that lasted for an impossibly small instant, yet shaped everything that followed. And as we drift deeper into the quiet mysteries of this early universe, another question naturally begins to rise. Part 8. Why we cannot travel to the edge. Even in imagination. Even if you sailed at the speed of light for 1 trillion years, the edge would always stay ahead of you. The expansion of spacetime outruns any ship, any photon, any dream. This makes the boundary partly philosophical, a limit defined not by location, but by what can ever be reached, measured, or known. When we imagine traveling through the universe, we picture something familiar, moving across a landscape, crossing distances, approaching faraway objects that sit patiently ahead of us. But the cosmos does not behave like a landscape. It behaves like a living fabric, constantly stretching, constantly widening the space between everything. In such a universe, far away is not a static condition. It is a moving target, a horizon that retreats as fast as we try to approach it. This is why traveling to the edge is impossible. Not because the edge is too distant, but because the act of traveling pushes it further away. No matter how fast you fly, even at the absolute cosmic speed limit, the expansion of spacetime always has a head start on the largest scales. The universe is not waiting for you. It is pulling itself open with every passing moment. The destination you aim for drifts away even as you move toward it. Imagine running across a field where the ground stretches beneath your feet. Every step you take is real. Every bit of progress is honest, but the field grows faster than you can cross it. The distance to the far side increases more quickly than your ability to cover it. You are not running toward a boundary. You are running inside something that expands as you run. This is what travel in the universe is like on cosmic scales. Even light, the fastest messenger nature has, cannot catch up to the regions where space-time expands faster than it can move. Those regions are not merely far. They are unreachable. Their distance grows too quickly for light to ever bridge the gap. This leads to a quiet but profound truth. There are places in the universe we can never visit, never see, and never know. Not because technology limits us, but because physics itself draws the boundary. If you launched a perfect spacecraft, one that could accelerate to near the speed of light, one that could coast forever without losing energy, and pointed it toward the farthest galaxy currently visible, you would discover that this galaxy is not waiting for you. It is receding. And not just receding. It is receding faster than you can approach it. The space between you expands more rapidly than your ship can close the distance. In this sense, the cosmic boundary is not a wall or a barrier. It is the expanding space itself. This horizon is called the cosmic event horizon, and it behaves differently from every horizon we know. The horizon on Earth is simply a limitation of perspective. The curve of the planet blocks your view. You can walk toward it, and it will draw closer. A cosmic horizon does not do this. No matter how far you travel, you never reduce its distance. It keeps extending, like a line drawn on water that flows away as you approach. 2. Imagine this more clearly. Picture a balloon marked with tiny galaxies. As the balloon expands, the galaxies grow farther apart. But if one of the galaxies attempted to move across the surface to reach a faraway one, the surface would keep stretching beneath it. No matter how fast it traveled, the expansion could outpace its motion. The horizon formed by this expansion is not a place. It is an effect, a limit born from motion, not from structure. This is why the edge of the universe cannot be reached even in imagination. If you visualize yourself racing toward the edge, what you are really visualizing is your path through space. But the edge is not located in space, it is located in time. It is defined by the limits of what light has had time to deliver, not by a physical coordinate waiting at the end of a journey. As you imagine yourself flying outward, the boundary moves outward with you. What you can see shifts, but the limits remain the same. You receive light from new regions, but the horizon of the knowable universe stays one step ahead, expanding as fast as you pursue it. The universe is not like a room with walls. It is like a story whose earliest pages are simply unwritten for you. Even the word edge becomes misleading. It suggests a place, a destination, a frontier that can be approached. But the edge is not a place. It is a condition. The boundary is defined by what can ever influence us, what can ever send a signal, a photon, a ripple in spacetime. Anything beyond that cannot touch us. It cannot send information. It cannot become part of our cosmic experience. This boundary is philosophical because it forces us to rethink distance itself. In ordinary life, distance means separation in space. If something is far enough, you can simply move closer. But cosmic distance is separation in spacetime. As time passes, the distance between 2 points is not constant. It changes with the growth of the universe. You cannot approach something that retreats not by motion, but by the expansion of the medium itself. Imagine sound waves in a room that steadily grows. When the room enlarges faster than sound can travel, there will be people you will never hear, no matter how loud they shout. Their voices are simply carried beyond your reach. In the universe, light acts the same way. The expansion creates silence, not silence from lack of activity, but silence from lack of connectivity. This silence is not empty. Beyond our cosmic horizon, stars burn, galaxies collide, black holes feed, planets circle their suns. Life may flourish or remain absent. Civilizations, if they exist, may look into their skies and see their own boundaries, centered on their own locations, shaped by their own reach of light. They, too, would find the edge unreachable. This is one of the most humbling realizations in cosmology. Every observer in the universe sees the edge moving away from them. Every point is surrounded by an expanding, unreachable frontier. It does not matter where you are. The horizon always lies beyond. And yet this boundary is quiet and gentle. It is not a tragic limit. It is a natural part of how spacetime behaves. A reminder that the universe is not a static structure, but a dynamic process, unfolding like a flower that blooms from its own center everywhere at once. Even in imagination, the edge cannot be reached because imagination itself relies on projecting motion through space. But the boundary is not about motion. It is about causality. It is about the ability of events to influence one another. And inflation, dark energy, and the accelerating expansion have permanently divided the universe into regions that will never interact. The edge is not a destination. It is a relationship between us and the limits of physics. This is why the boundary is partly philosophical. It defines not where the universe ends, but where our story ends. It marks the limits of what can ever enter our experience. It is the line between what is part of our cosmic history and what lies forever outside our narrative. And yet, beyond that boundary, the universe is still real, still active, still vast. It is simply not ours to reach. And as we drift deeper into this reflection, another quiet mystery begins to unfold. Part 9. Could the universe be finite yet unbounded? It is possible, according to general relativity, for the universe to be finite in volume but have no edge at all, like the surface of a sphere but extended into 3 dimensions. You could travel forever and never reach a border, looping through space in a vast cosmic geometry. Whether our universe has such a shape remains one of cosmology's quiet, open questions. To begin imagining this, think about the surface of the Earth. You can walk in a straight line around the planet and never encounter a wall or a boundary. You never find an edge where the surface simply stops. Instead, you move across a continuous curved world that eventually returns you to your starting point. The surface is finite, yet unbounded. It has a limited area but no edges. Now, imagine this idea not in 2 dimensions, but in 3. A space that curves back on itself the way the surface of the Earth does, but in every direction of volume. This is what cosmologists mean when they consider a universe that is finite yet unbounded, a cosmos that loops through itself. In such a universe, if you traveled far enough in a straight line, moving always forward, never changing direction, you might eventually return to where you began, not because you turned around, but because space itself was curved. There would be no frontier, no border, no cosmic cliff, just an endless journey across a seamless geometry. And yet, while this idea sounds abstract, general relativity allows it. The equations describing spacetime do not require the universe to have boundaries. They do not require infinite extent. They allow for shapes that are closed in on themselves, like the surface of a sphere, or more complex shapes such as toroidal or multi-connected geometries. In these geometries, space does not need an outside. It contains itself. This is one of the most subtle and beautiful possibilities in cosmology. The universe might be finite, yet without edges, complete, yet without borders, bounded, yet entirely self-contained. The reason this idea arises from general relativity is that gravity curves spacetime. Mass and energy tell space how to bend, and space tells matter how to move. This curvature shapes not only the local environment around stars and galaxies, but also the global shape of the universe itself. Depending on the amount of matter, the presence of dark energy, and the initial conditions of the Big Bang, space-time can curve in different ways, positively, negatively, or remain nearly flat. A universe with positive curvature could take a spherical form, finite, smooth, closed. A universe with zero curvature would be flat, possibly infinite, but not necessarily. A universe with negative curvature would expand endlessly like a saddle shape, again, possibly infinite. Because each possibility fits the equations, determining the true shape of the universe becomes an observational challenge, not a theoretical one. One of the tools we use to discern this shape is the cosmic microwave background. By measuring the angular scale of temperature fluctuations across the sky, scientists can infer how light has traveled through spacetime. If the universe curves significantly, those patterns would appear distorted. Straight lines would behave subtly differently. The geometry would leave a trace. So far, the evidence suggests that the universe is extremely close to flat, so close that if it curves, it must do so over a scale far larger than anything we can observe. But flat does not necessarily mean infinite. A flat sheet of paper is infinite in theory, but can also be wrapped into a cylinder or torus in practice. Both shapes are finite, but have no edges. A universe can be mathematically flat, yet physically closed if space wraps around itself in a multi-connected topology. In such a topology, traveling far enough in a straight line could bring you back to your origin without encountering a boundary. Cosmologists have searched for such signatures, patterns in the cosmic microwave background that repeat, faint echoes of light seen from different directions, like seeing the same mountain reflected in multiple mirrors. If the universe were multi-connected on scales comparable to the observable region, we might detect such repetitions. So far, no repeating patterns have been confirmed, but the absence of evidence does not rule out the idea. It only means that if the universe is finite and unbounded, its scale is larger than what our horizon can probe. Another reason this question remains open is that the observable universe is limited by the speed of light and by cosmic expansion. We can only see a spherical region around us, roughly 46 billion light-years in radius. But the universe could extend billions or trillions of light-years beyond that, or it could loop back on itself in a shape far too grand for us to detect. The horizon hides the evidence. When we look outward, we see only a portion of the universe, not its full shape. It's like standing on a small patch of the Earth and trying to deduce the planet's curvature using only the landscape around you. The terrain might appear perfectly flat over short distances, giving no clue that the Earth is round. Likewise, the very flatness of our observable region makes it difficult to determine whether space wraps around itself on enormous scales. This leads to one of the quietest truths in cosmology. We do not know the global shape of the universe, and we may never know it fully. But this uncertainty is not a failure. It is a reminder of the scale on which the universe operates. The cosmos may be too large, too subtle, or too gently curved for our position in time and space to reveal its whole form. If the universe truly is finite and unbounded, then space folds in on itself like a cosmic labyrinth with no exit and no outer wall. Every direction leads inward, not outward. Every path loops through the geometry rather than escaping it. There is no need for an outside because the universe contains all the space that exists. And if the universe is infinite, then it stretches beyond anything we can imagine, without repetition, without looping, without end. Both possibilities are equally profound. Both speak to the vastness of the cosmos and the limits of human intuition. Yet there is comfort in the idea of a finite yet unbounded universe. It offers a vision of completeness without isolation, a universe that holds itself gently like a sphere suspended in possibility, a cosmos where motion is eternal but boundaries do not confine. In such a universe, every traveler, real or imagined, journeys through a landscape that curves quietly beneath their path. They may fly for eons without ever sensing the curvature. They may explore forever without finding an edge, but the space they travel remains whole, entire, self-enclosed. This geometry also aligns beautifully with the cosmic principle that no point in the universe is special. If the universe curves in a closed shape, then every point is equivalent. There is no center, no privileged location, no outer boundary, only a global symmetry woven into the fabric of reality. Whether the universe has this shape remains an open question, a gentle puzzle at the intersection of mathematics, geometry, and observation. But the possibility itself is soothing. It suggests a universe that is at once mysterious and harmonious, a universe that needs no outside to exist, a universe complete enough to loop through itself, yet vast enough to escape comprehension. As we drift deeper into this cosmic geometry, another quiet question begins to unfold. Part 10. Why light itself sets the limits of what we see. When we look deeper into the universe, we are also looking backward in time. The speed of light is both fast and finite, and that finiteness creates a natural wall around our knowledge. The edge is not a place, but a time, a limit carved by how long light has been able to travel since the universe first began to shine. This simple truth lies at the heart of every cosmic horizon. It means that the deeper we peer into space, the older the universe becomes. Every distant galaxy is a memory. Every faint glow is a message. Every beam of ancient light is a traveler carrying the story of a younger cosmos. When we gaze across millions of light years, we see galaxies as they were millions of years ago. When we look across billions of light years, we witness cosmic structures as they formed when the universe was still new, still cooling, still discovering its own shape. Light doesn't just illuminate space, it illuminates time. This is why astronomy is an act of archaeology. We do not study the universe as it is now, not directly. We study it as it was. Our telescopes are time machines, but only because light takes time to travel, and that travel time creates a boundary. No matter how perfect a telescope becomes, it cannot see beyond the age of the light reaching it. If a galaxy is 10 billion light years away, its light took 10 billion years to arrive. We see it as it was when Earth itself had not yet formed. The image is not delayed because the galaxy is playing a trick on us. It is delayed because that is how long light requires to cross the expanding ocean between us. The universe is filled with countless stories, but we can only read the ones whose light has had enough time to reach our eyes. This is what cosmologists mean when they talk about the observable universe. It is not the entire cosmos, it is simply the region where light has completed the journey. A sphere centered around us, not because we are special, but because we are the ones making the measurement. The radius of that sphere is set by time, by the age of the universe, by the speed of light, nothing else. Because the universe has a beginning, the reach of light is finite. And because light moves at a fixed speed, about 299,792 kilometers per second, there is only so far it can have traveled since the Big Bang. This creates a cosmic horizon, not unlike the horizon at sea. The Earth does not end where the ocean meets the sky. That boundary is an illusion created by perspective. Likewise, the universe does not end at our cosmic horizon. That boundary is created by the travel time of light. Beyond that horizon lies more universe, vast, real, unreachable, silent. But the horizon is not fixed. It grows with time. Every second, light from slightly more distant regions arrives, expanding the boundaries of what we can see. The observable universe grows larger, but the universe itself grows even faster. The horizon is always changing, always receding, always evolving. If the speed of light were infinite, none of this would be true. We would see the entire universe instantly, as a single cosmic snapshot. There would be no deep past to uncover, no delayed messages, no layered history of galaxies forming and stars igniting. The night sky would be static, timeless, frozen. But the speed of light is finite, and that finiteness gives the universe a story. Because of light's limited speed, we can watch galaxies evolve across time. We can observe them when they were young, bright, chaotic. We can watch them become mature, calm spirals. We can witness them collide, merge, and reshape themselves. Without the delay imposed by light, none of these cosmic narratives would be visible. The finiteness of light also creates the strange realization that the universe appears different in every direction, not because the cosmos is varied, but because we are seeing it at different ages. In some directions, we see more nearby galaxies, more recent moments. In others, we see deeper into time, glimpsing the universe as it was billions of years ago. And in every direction, if we go far enough, we eventually see the cosmic microwave background, the faint afterglow from when the universe first became transparent. This is the deepest layer of light the cosmos has to offer, not because it is the farthest point in space, but because it is the farthest point in time. Before that, the universe was opaque. In this way, time itself becomes the universe's most profound boundary, but light imposes another limit as well. Because the universe is expanding and expanding faster over time, there are distant galaxies whose light will never reach us, no matter how long the universe continues. The space between us grows too fast. The photons are carried away as surely as a message tossed into a rising tide. They never move backward, never turn around, never find their way home. Those regions are not just unseen, they are unseeable. This introduces two types of horizons: the particle horizon, what light from the past has already reached us. This defines the observable universe. The event horizon, what light from the future will never reach us. This defines what can ever become part of our cosmic knowledge. Light draws both lines. One is an expanding shell of information from the ancient past. The other is a shrinking window of what can ever be learned. Together, they form the limits of our cosmic story. Another way to imagine this is to think of raindrops falling on a pond. The ripples expand outward at a steady rate. If you stand at the center, the ripples that reach you mark the boundary of what you can detect. Any raindrop that falls too far away will create ripples that never arrive. Not because you are too weak to feel them, but because the pond grows beneath you, stretching faster than the waves can travel. The universe behaves similarly. Cosmic expansion outruns some of the waves. Light itself becomes powerless in the ideachu. Race against expansion. Even the fastest signal nature allows loses to the growth of space. This is why the edge of the universe cannot be crossed. It is created by the rules of time, by the limits of causation, by the finite speed at which information travels. Light carries the universe's messages, but it cannot deliver them when the fabric between sender and receiver grows too fast. That is why distant galaxies fade into invisibility, why the cosmic microwave background forms a wall of brightness, why the earliest moments after the Big Bang remain forever hidden. This limitation is not a flaw. It is a feature, a fundamental part of how reality organizes itself. Because the speed of light is finite, the universe is layered. Because the speed of light is finite, the night sky holds ancient memories. Because the speed of light is finite, we can trace the universe's evolution, step by step, glow by glow, photon by photon. Even the stars overhead are part of this story. Some shine from trillions of kilometers away. Others shine from billions of light years away. Each one is a glimpse into the past. And when you realize that everything you see is a message delayed by the speed of light, the night becomes something more than a view. It becomes a history, a record, a map of the universe written across time. In this cosmic sense, the edge is not something you can approach. It is something that recedes with every moment, woven from the travel limits of light. The boundary is not out there. It is within the laws of nature themselves. And as we drift deeper into this universe shaped by light and time, another quiet question begins to rise. Part 11. What happens at the edge of cosmic structure? As we journey outward in maps of galaxies, we see clusters, then filaments, then vast cosmic voids. But eventually, structure thins as we approach the horizon where light cannot reach us. This thinning is not a true boundary, but a transition from the observable universe to the unobservable one, a gentle fading of information, not of existence. To understand this thinning, imagine you are walking through a dense forest. Near the center, the trees crowd around you, lush and close. But as you move toward the edge of your vision in the morning fog, the trees appear to thin not because the forest ends, but because the fog hides their outlines. The forest continues, but your sight fades. The universe behaves the same way. The cosmic structures we see, clusters, walls, filaments, become less detailed not because they cease to exist, but because the light carrying their stories grows faint or fails to arrive. The structure of the universe on large scales forms what cosmologists call the cosmic web. It is a sprawling network of galaxies arranged like droplets of dew on threads of gravitational silk. These filaments span hundreds of millions of light years, bridging clusters of galaxies, arching over deep cosmic voids, forming a pattern both chaotic and deeply ordered. It is the largest structure ever mapped, a quiet architecture shaped by dark matter and the relentless pull of gravity. As we move outward through this cosmic web, we find that galaxies cluster into groups. Groups connect into filaments, and filaments weave into walls like the Sloan Great Wall or the Hercules Corona Borealis Great Wall, immense structures spanning billions of light years. These forms do not arise randomly. They are the frozen imprint of ancient fluctuations amplified by gravity over billions of years. But the farther we look, the fainter these structures become, not because they end abruptly, but because the universe is finite in age. The farther away a galaxy is, the longer its light has traveled. And the longer its light has traveled, the more stretched it has become due to cosmic expansion. Eventually, that stretching dims the light beyond the sensitivity of our instruments. And beyond a certain distance, the expansion outruns the photons entirely. This is why cosmic structure thins at the horizon. It is not a disappearance, it is a dimming. What we call the edge is not a change in the universe, but a change in our ability to observe it. If you could stand outside the limits of time and look at the universe as a whole, not from a single galaxy, but from an impossible vantage point outside the fabric itself, you would see the cosmic web continue far beyond the horizon we perceive. You would see filaments stretch into the darkness, clusters linked like beaded necklaces woven by gravity's hand. You would see voids, immense regions containing few galaxies, connected to one another like bubbles in a cosmic foam. But from where we stand, separated by distance and time, this vast architecture fades softly as it approaches the limits of what light can deliver. This subtle thinning tells us something important. Our cosmic map is incomplete, and it will always remain incomplete. Even as our telescopes grow sharper, even as technology improves, the horizon moves with time, revealing new regions while hiding others forever. The cosmic web extends far beyond what we can chart, not because the universe hides it from us intentionally, but because expansion removes parts of the cosmos from our future. The behavior of the cosmic web near the horizon reveals another feature. The structure of the universe is remarkably uniform on large scales. If you zoom out far enough, differences fade. Clusters look similar. Filaments repeat their patterns. The distribution of galaxies becomes statistically uniform. Cosmologists call this homogeneity. It means that while the universe has structure, that structure does not favor any region. It repeats across vast distances, giving the cosmos a balanced, even rhythm. Because of this homogeneity, when the structure begins to fade near the horizon, it does not do so abruptly. It fades softly, as though dissolving into the limits of visibility. The cosmic web does not end. Our view ends. This transition carries a quiet significance. It reminds us that our perspective is not the universe's truth. It is a small slice illuminated by light that has completed the journey to our eyes. Beyond the horizon, galaxies continue to evolve. Stars live and die. Planets orbit stars we will never see, maybe carrying life we will never know. The cosmic web, with its filaments and voids, stretches quietly through those regions. The structures are there, real, gravitational, ancient, and yet forever invisible to us. And this invisibility deepens over time. The accelerating expansion of the universe causes distant galaxies to drift away faster. The cosmic web, beyond a certain distance, becomes permanently unreachable. Light from those galaxies will never overcome the expansion of space, never catch up, never arrive. Those regions do not simply fade, they are erased from our future. In this way, the thinning of the cosmic web is also a thinning of connection, a gentle severing of what the universe can show us, a soft limit on what will ever enter our cosmic story. But even at the edge of observability, the cosmic web reveals hints of its deeper nature. Studies of galaxy clustering show that filaments extend smoothly past the horizon, implied by current observations. The distribution patterns we detect near the furthest reaches of the sky match what theory predicts should continue beyond. There is no sign that structure stops or changes abruptly. This is powerful evidence that the universe remains connected and patterned, far beyond what we can see. Another way to understand this thinning is to think of it as looking into a fog that grows denser with distance. In a valley on a foggy morning, you can see the trees near you clearly. A bit farther, they appear faint. Beyond that, they dissolve into silhouettes, then into shapes, then into nothing. The forest continues. Your vision does not. The cosmic fog is not made of vapor, of course. It is made of time, distance, and expansion. Light weakens as it stretches. Photons lose energy. Redshift turns visible light into infrared, then into microwaves. Eventually, objects fade from sight not because they cease to shine, but because the universe stretches their light beyond detection. The cosmic microwave background, the faint glow from the early universe, is the ultimate manifestation of this thinning. It is the surface where structure becomes invisible to light because the universe was too dense to allow photons to travel freely. Beyond that moment, We cannot see structure at all, and even the cosmic web itself may have a role in shaping these limitations. Large-scale structures gravitationally lens light, distorting what we see near the horizon. The bending of spacetime by clusters, filaments, and dark matter warps the path of photons on long journeys. Near the edge, these distortions become increasingly subtle but increasingly important. They add to the sense of thinning, not because structure fades, but because our view becomes more distorted. In this way, the edge of cosmic structure is a blend of physical limitations and geometric illusions. It is a place where light grows too faint, too redshifted, too distorted. A place where the universe's map fades, not because the terrain ends, but because the light that draws the map cannot reach us. What happens at the edge of cosmic structure is not a dramatic cutoff. It is a soft gradient from clarity to silence, a gentle dimming of galaxies until they dissolve into the horizon, a transition from observable structure to inferred structure. And yet, the thinning carries a quiet comfort. It reminds us that the universe is larger than the part we can see. It assures us that the cosmic web continues endlessly, weaving its delicate pattern beyond our reach. It whispers that the universe does not end where our sight ends. Our limitations are not its limitations. As we drift deeper into the cosmic horizon, another question, soft, ancient, inevitable, begins to form. Part 12. Why some regions of space will never be visible to us. Because space expands faster than light on large enough scales, vast regions will remain forever beyond reach. Their light will never arrive no matter how long we wait. In a sense, these regions are part of our universe, but not part of our cosmic story. Their silence is permanent. To understand why, imagine standing at the edge of a great ocean. Waves ripple toward you from near and far, each one carrying a memory of where it formed. The water stretches endlessly, and somewhere out on its horizon, storms you will never witness are stirring. They produce waves too faint, too distant, too delayed to ever reach your feet. They are real, but their energy will never touch you. The universe is like this ocean, except that the waves are light and the sea itself is space-time. The expansion of the cosmos stretches this sea so quickly that some waves never complete their journey. The light that begins traveling toward us from extremely distant regions is caught in a race it cannot win. Space grows beneath it. The distance increases faster than the photons can close it. The message is lost before it can even begin to arrive. This permanent separation is what cosmologists call the cosmic event horizon. It is the ultimate boundary, not of the universe itself, but of what is knowable. Inside the event horizon are all the regions whose light will someday reach us. Outside are those that never will. This is one of the quietest, most humbling facts in all of astrophysics. We live in a universe where most of the cosmos is permanently invisible, not temporarily hidden, not simply waiting for more time to pass, but permanently cut off, as though divided by a deep and irreversible silence. The cause of this silence is not distance itself, it is the accelerating expansion of space-time. Dark energy, the mysterious force driving this acceleration, causes the fabric of the universe to stretch exponentially. Every second, more distant regions slip over the event horizon, never to return. Their light is swept away by the growing sea of space-time, carried outward like a message in a current that strengthens with time. This means that even now, as you breathe quietly, galaxies are vanishing from our future sight, not disappearing from existence, but drifting beyond the reach of our cosmic connection. Their last photons are on their way toward us, but once they pass, no new ones will replace them. We will see them grow fainter, then redder, then invisible, and then silent forever. This is not a metaphor. It is the direct consequence of Einstein's equations, which describe how the expansion of space affects the travel of light. As the universe accelerates, space between distant objects stretches so fast that even light moving at 299,792 kilometers per second becomes powerless. The photons are not slow, the space is too fast. This phenomenon leads to something subtle but profound. Most galaxies in the universe are already unreachable. Even if we could travel at 99.99% the speed of light, even if we could journey indefinitely, there are regions where we would never arrive. Not because our ships are too weak, but because space-time itself prevents the journey. This transforms our understanding of the cosmos. The universe we can explore, even in principle, is only a small fraction of what exists. The rest continues evolving outside our horizon. Stars ignite, galaxies collide, black holes form, planets orbit their suns, and perhaps life stirs in places whose light will never touch our skies. It is strange to imagine that there are civilizations, if they exist, whose entire cosmic story will never intersect with ours. They may look upward and see their own horizon, their own thinning of structure, their own fading galaxies. And they would never know we are here. Their silence to us is matched by our silence to them. This distance is not emotional, it is physical. It is built directly into the geometry of space-time. It also means that our observable universe is shrinking in a particular sense. While the particle horizon expands as more ancient light arrives, the event horizon contracts relative to our ability to interact. The region from which we can ever receive new light becomes smaller over time. Our future sky will be emptier, quieter, darker. This fate is sometimes called the cosmic isolation of the far future. Eventually, only the galaxies gravitationally bound to us, our local group, will remain visible. Everything else will fade beyond the event horizon. The Andromeda Galaxy, the Triangulum Galaxy, and several dozen dwarf galaxies will become the only islands of light in an expanding dark ocean. The grand cosmic web will disappear from sight, leaving future astronomers, trillions of years from now, unable to infer the true nature of the universe. In their telescopes, the cosmos will appear, static and small. They will not see the cosmic microwave background. They will not see galaxies rushing away. They will not detect the expansion of space. They will not know the universe began with a Big Bang. All of that information will fade past the horizon into permanent silence. Our generation, and the generations near us in cosmic time, live in a brief and precious window when the universe is still readable, when the sky still carries messages from the early cosmos, when the cosmic web is visible, when the microwave background glows faintly, when the accelerating expansion has not yet erased the evidence. We live at the moment in cosmic history when the universe can still tell its story. This is why some cosmologists call this epoch observationally privileged, not because humans are special, but because this era is uniquely rich in information. The universe is transparent. The horizon is still nearby. The cosmic microwave background still sings. The galaxies are still close enough that their light survives the journey. But this window will not last forever. The event horizon will continue sweeping regions away until the universe is left with only a tiny remnant of what once was, a miniature sky in comparison to today, a sky where the vastness of the cosmos is hidden behind the accelerating flow of space-time. This reveals something gentle yet profound. The universe hides its future from us just as surely as it hides its most distant regions. There are corners of space-time we will never reach, moments we will never witness, structures we will never map, light we will never receive. And yet these unreachable regions are part of the same universe. They are real, filled with matter, gravity, and motion. Whether or not we can see them does not change their existence. This creates a curious duality. The universe is one whole, but our experience of it is limited. We see only a sphere carved out by time and light. Beyond that sphere, the cosmos continues without us. It is like standing at the center of a dimly lit room where a candle illuminates only a small circle. Outside that circle lies the same space, but in darkness. The room does not end where the light ends, only your view does. So as we contemplate the regions we cannot see, the ones forever beyond our horizon, it is important to remember that their silence is not hostile. It is not a void. It is simply the quiet imposed by the laws of physics. a quiet woven into the universe from the moment inflation began. A quiet carried forward by dark energy, a quiet that will deepen as space-time expands. Their silence is permanent, but their existence is part of the same cosmic tapestry we inhabit. And as we drift into the mystery of this unreachable universe, another question softly begins to rise. Part 13. Does the universe have an actual physical edge? No known theory predicts a hard physical border. Instead, the universe likely extends in directions we will never see, shaped by dark energy, geometry, and the laws of space-time. If an edge exists, it is not a place but a limit to measurement, a horizon engraved not in space, but in physics itself. This is one of the strangest truths about the cosmos. We grow up surrounded by boundaries, walls, shorelines, fences, horizons. Everything in our everyday lives has an outside, a container, a limit. Every city ends, every map ends, every object has a surface. So it feels natural to imagine that the universe must have one too. Some cosmic boundary we could, in theory, reach if we traveled far enough. But the universe does not behave like the objects within it. It is not a thing contained inside something larger. It is the container itself. If you could drift through space for billions of years, passing galaxies, traversing voids, crossing the cosmic web, you would never encounter a sign or a wall or a frontier. Galaxies would thin with distance, then vanish from visibility, but the thinning would not mark a physical ending. It would mark the edge of what light can show you, not the edge of what exists. Physics draws a gentle distinction between two ideas, the boundary of our observations and the boundary of the universe itself. So far as we can tell, only the first one exists. You can imagine the observable universe like a bubble of knowledge around us, expanding slowly as more ancient light arrives. But beyond that bubble, the universe continues. It does not fold inward. It does not crash into a cosmic barrier. It simply extends into regions forever inaccessible to us, regions carved away by the limits of light, distance, and the accelerating expansion of space-time. This is why cosmologists speak in terms of horizons rather than physical edges. A horizon is not a location. It is a limit, one whispered by the mathematics of relativity, not by the presence of a boundary in space. The particle horizon marks the farthest distance from which light has reached us since the Big Bang. The event horizon marks the farthest distance from which light will ever reach us in the future. Both horizons are products of time, age, and expansion, not physical walls. Still, the idea of an edge tempts the imagination. If the universe began with the Big Bang, doesn't that imply a central point? If galaxies are moving apart, doesn't that imply something they expand into? If the universe is finite, must it not have a border? These are reasonable questions shaped by intuition, but intuition struggles in the face of cosmology. Our senses evolved to navigate landscapes, not space-time. The first challenge lies in the nature of the Big Bang itself. It did not occur at a point in space, it occurred everywhere at once, because space itself was compacted into an unimaginably small state. When the universe expanded, it expanded uniformly, not from a location, but from a condition. Every region of today's cosmos traces its origins back to the same dense beginning, and no region holds a privileged position. Because of this, the idea of a central point simply does not apply. The second challenge is understanding that space is not embedded in something larger. The universe does not expand into anything. Instead, expansion refers to the increasing distance between points in space. It is a change in geometry, not a motion through a medium. Imagine drawing dots on a balloon and inflating it. The dots grow farther apart, yet they do not move into anything. The surface they inhabit is all the space they know. To ask what lies outside the surface is to step outside the analogy. In the real universe, there may be no outside at all. Space is not a substance floating in another substance. It is the framework within which all substances exist. The third challenge lies in the possibility that the universe might be finite yet unbounded, like the three-dimensional analog of a sphere's surface. In such a cosmos, space loops through itself. There is no border to hit, no edge to fall from, no external region to reach. You could travel indefinitely and never find a frontier. You would simply keep moving through a self-contained geometry. Even if the universe is infinite, the situation is similar. No edge, just more space. Infinity does not require borders. It simply requires that the landscape never ends. But the deepest challenge is recognizing that all of this remains partially hidden. Our ability to map the universe depends on light, and light depends on time. Because the universe has a finite age, we can only see a finite volume of it. And because the expansion is accelerating, some regions slip permanently beyond our view. What we see is only a tiny fraction of what exists, and what exists may be structured in ways we cannot infer from the part we observe. In this sense, asking whether the universe has an edge is like standing in a dark valley with a small lantern and asking whether the world ends where the light stops. The boundary you see is the boundary of your lantern glow, not of the earth. The cosmic microwave background offers the most ancient light the universe allows. It is the oldest visible chapter. Beyond it lies an era the universe keeps hidden, the first few 100,000 years when light could not travel freely. Beyond that lies another hidden region, places where inflation stretched space-time so far, so fast, that their light has been forever carried away. And beyond that lies a deeper hidden frontier, regions where the expansion simply outruns any future possibility of connection. These are boundaries of observation, not of existence. If a physical edge exists, some literal border of space, it would be a truly radical discovery, requiring new physics far beyond general relativity. None of our current theories predict such an edge. None of our measurements require it. No observation hints at it. Every piece of evidence suggests continuity, not termination. But cosmology is humble. It does not assert what it cannot prove. It simply describes what the universe allows us to witness. The edge we speak of, the only edge we know, is carved into the limits of measurement. It is etched by the finite speed of light, the age of the cosmos, and the expansion of space. It is a horizon of information, a boundary shaped by what light can reveal and what physics permits. Beyond that horizon, the universe may stretch endlessly, or it may fold back on itself, or it may take a shape we cannot yet imagine. But whatever the true nature of the cosmos, the quiet truth remains. The edge is not a surface, it is a silence woven into the universe's laws, a silence that deepens with expansion, a silence that marks not the end of reality, but the end of our reach. And as we drift toward the final mysteries of this cosmic boundary, a new question, soft, ancient, and inevitable, begins to take shape. Part 14. Could the universe beyond our horizon be different? Some models suggest that conditions beyond the observable universe might vary. Regions with different densities, different patterns of galaxies, or even different cosmic histories. Inflation allows such variation, but gently. Most predictions say the universe beyond our sight is familiar, repeating the same cosmic texture we see around us. This question touches one of the deepest, softest mysteries in cosmology. What lies beyond the part of the universe we can ever know? Not just beyond our maps, but beyond all possibility of observation, beyond the reach of light itself, beyond the horizons defined by physics. When we ask whether the distant cosmos might differ from the universe around us, we step into a realm where science becomes a blend of evidence, inference, and quiet humility. What we see in the observable universe suggests remarkable uniformity. Zoom out far enough, billions of light years, and galaxies arrange themselves in the same intricate web everywhere we look, clusters connected by filaments, filaments bordering voids, voids opening into deeper emptiness. This pattern holds across vast swaths of space. It holds in every direction. It is the cosmic fingerprint of inflation and gravity working together over billions of years. But our observable universe is only a small part of the whole. Perhaps a tiny part, perhaps an unimaginably minuscule island in a sea much larger than we can fathom. So the question becomes, is the rest of the ocean similar to the shore we can see, or does it change as we sail into the fog? Inflation offers the first clue. According to this theory, the universe expanded so rapidly in its earliest moments that any irregularities, any lumps, bumps, distortions, or variations were smoothed over on enormous scales. Like stretching a sheet of fabric so tightly that wrinkles disappear, inflation made the universe nearly uniform across regions vastly larger than our horizon. This smoothing acts gently but relentlessly. As a result, even regions we will never observe directly are predicted to share the same broad properties, the same average density, the same laws of physics, the same cosmic makeup of dark matter, dark energy, and ordinary matter, and the same statistical texture of galaxies forming along filaments. In other words, inflation predicts that the universe is, on average, the same everywhere, even if small fluctuations differ from place to place. But the same does not mean identical. Quantum fluctuations, stretched to cosmic scales during inflation, became the seeds of large-scale structure. These fluctuations were random, tiny differences in density that later grew into galaxies, clusters, and cosmic voids. Because they were random, regions beyond our horizon almost certainly bear different specific patterns, different cluster arrangements, different filament shapes, different superclusters, and voids. Their cosmic web is familiar in form, but not in detail. It is like walking through a vast forest. Every section of the forest contains trees, undergrowth, and winding paths. But the specific arrangement, the exact shape of each clearing, the positions of each tree, is unique to each region. The pattern repeats broadly, but never exactly. The universe may be the same way. Some models go further. They suggest that even the broad properties might vary slightly. Inflation, especially in its more complex versions, allows for pockets of spacetime that experience slightly different conditions. These variations would be subtle, perhaps slight differences in average density, slight differences in the amplitude of initial fluctuations, or gentle shifts in cosmic temperature. Nothing dramatic, nothing that would rewrite the laws of physics, but small changes that might alter the architecture of structure on the largest scales. Still, these differences would remain within the same cosmic family. They would not produce wildly unfamiliar universes. They would still be galaxies and clusters and voids, just arranged differently. More speculative theories extend this idea even further, proposing the existence of bubble universes, or regions where inflation ended earlier or later, creating pockets with different physical constants or histories. But these models belong to the realm of multiverse hypotheses, intriguing, poetic, mathematically possible, but lacking direct evidence. They are conversations at the edge of science, not conclusions drawn from observation. The more grounded models, the ones most consistent with the data, paint a gentler picture. They tell us that the universe beyond our horizon is likely familiar, echoing what we see locally, shaped by the same physics, governed by the same laws. This prediction rests on two pillars, observations and symmetry. The first pillar, observations, comes from the cosmic microwave background. Its near-perfect uniformity tells us that the early universe was extraordinarily even. Tiny variations in temperature and density exist, but their distribution follows a statistical pattern that inflation predicts, a pattern that should continue far beyond the observable region. The second pillar, cosmic symmetry, comes from the idea that the universe is homogeneous and isotropic on large scales. This cosmological principle is not just a philosophical choice, it is supported by everything we see: galaxy surveys, brightness distributions, cosmic microwave background measurements, gravitational lensing, and large-scale structure maps. Every measurement points toward sameness, not monotony, but balance throughout the vast expanse. Together, these pillars suggest that the universe beyond our horizon is a continuation of what we see. Immense filaments, deep voids, swirling clusters, star-forming galaxies, quiet dwarfs, ancient ellipticals, and perhaps even regions rich with structures we can never imagine. But even if the universe repeats its texture on large scales, there remains an unavoidable truth. We will never know its details. Because the cosmic event horizon shrinks the future of what we can observe, there are entire regions of the universe whose light will never reach us. Their galaxies will never grace our telescopes. Their clusters will never appear in our maps. Their histories will never join ours. They exist beyond what light can carry, beyond what expansion allows. This creates a philosophical tension. The universe continues beyond our horizon, real, active, intricate, but it becomes forever inaccessible. We can infer its nature, but never confirm it. We can imagine its landscapes, but never observe them. We can predict its structure, but never map it. In this sense, the universe beyond the horizon exists in a liminal state, real but unreachable, predicted but unmeasured, familiar but unknown. Still, the gentleness of inflation's predictions offers comfort. It suggests that the cosmos does not transform into something alien just outside our view. It does not hide strange geometry or radically different physics, a breath beyond our reach. Instead, it continues the same cosmic story: the growth of structure, the rise of galaxies, the expansion of spacetime, the quiet interplay of gravity and dark energy. Even if the details differ, the melody remains. This idea invites a subtle, soothing reflection. What we see in the night sky is not a special corner of the universe. It is one expression of a universal pattern, a pattern that repeats like a cosmic heartbeat, pulse after pulse, horizon after horizon. And yet, the mystery remains open, not because the universe refuses to reveal itself, but because the laws of physics gently limit what light can tell us. As we drift deeper into this question, into the possibility of familiar structures beyond sight, another cosmic curiosity begins to unfold. Part 15. The Cosmic Boundary Paradox. Here lies the paradox. The universe might be infinite, yet we can only see a fraction. The edge is also not an ending, but a limit to knowledge. And as cosmic expansion accelerates, that limit grows, pulling more of the universe beyond our reach. The more the universe expands, the less of it we will ever see. The horizon widens, but the knowable world slowly shrinks. This paradox is one of the most profound in all of cosmology. It challenges our intuition, our sense of exploration, and our understanding of limits. In everyday life, the more we step forward, the more of the world we see. Horizons expand as we move. Mountains rise into view. Forests open. Oceans reveal their breadth. But on cosmic scales, the rules are different. The horizon is not something we can chase. It recedes faster than we can approach it. The universe grows, but our window onto it constricts. It is as though the cosmos is a vast library whose shelves extend forever, yet the light illuminating those shelves dims with time, revealing fewer volumes as the hours pass. The books are still there, still full of stories, still full of meaning, but they slip into darkness, unreachable. To understand this paradox, imagine the observable universe as a bubble around us. Not a physical bubble, but a bubble of light. Its size is determined by the time since the Big Bang and the speed of light. As time passes, the bubble grows, because more ancient light has had time to reach us. At first glance, this suggests we should see more of the universe as time progresses, and in a way, we do. Each moment, distant photons, emitted billions of years ago, finally complete their journey. They add new layers to the tapestry of our sky. The bubble expands, embracing slightly more of the cosmos. But expansion introduces a complication. Space-time stretches, the distance between galaxies grows, and that stretching accelerates because of dark energy. The universe is not just expanding, it is expanding faster with time. This acceleration has consequences. As the cosmos grows, parts of it recede faster than light can travel. They drift beyond what physicists call the cosmic event horizon, the boundary separating the regions that will one day send us light from those that will never send us anything again. So while the observable universe grows due to light arriving from the past, the event horizon shrinks relative to what we can ever know in the future. Beyond that horizon, galaxies disappear from our potential cosmological story. They continue to exist. They continue to evolve. but their future influence on us is severed. This is the paradox in gentle, unavoidable form. The knowable universe grows and shrinks at the same time. We see deeper into the past than ever before, yet our ability to know the future of distant regions fades. The cosmic horizon expands outward, while the cosmic event horizon closes inward. Two horizons, each shaped by light and expansion, moving in opposite directions. This tension lies at the heart of the cosmic boundary paradox. To visualize it more clearly, imagine Orb-P standing in a wide meadow at dawn. As the sun rises, the fog lifts near you, revealing more of the landscape. Distant hills appear one by one, but at the same time, a deeper fog settles beyond the farthest ridge, obscuring the mountains beyond. You can see a growing circle of terrain around you, but the world outside that circle fades into deeper unreachability. This is our place in the universe. Even now, as we observe galaxies farther away than ever before, those galaxies are simultaneously slipping out of our causal future. The light we receive today may be the last message we will ever receive from them. Their future light will be swept away by the accelerating expansion, unable to bridge the growing gulf. This is not merely speculation. It is written into the mathematics of relativity. The solutions that describe an accelerating universe predict an event horizon, a limit beyond which information is permanently inaccessible. The universe is expanding so quickly that the rate of separation in some regions exceeds the speed of light. And while nothing can move through space faster than light, space itself can expand at any rate. The photons, racing tirelessly, cannot overcome the widening gulf. In this sense, the boundary paradox is not only about what we can see today, but what we will never see tomorrow. There is a deep irony here. Humanity builds larger telescopes, develops sharper detectors, launches more powerful observatories. We enhance our senses with technology, reaching farther into the cosmos with each generation. And yet, the cosmos withdraws from us at the same time. Not out of malice, not out of mystery, simply out of the geometry of spacetime. The more the universe grows, the more it hides. This paradox also reshapes how we think about infinity. If the universe is infinite, then the fraction we can ever know becomes infinitely small. Our observable universe becomes a vanishing sliver within an unending expanse. But even if the universe is finite, the horizons still limit what we can observe. A finite universe with a shrinking horizon becomes more mysterious over time, not less. The map of the cosmos we hold today will one day represent only a ghost of what once was visible. Future civilizations, millions or billions of years from now, will live in a universe darker and lonelier than ours. The night sky will contain far fewer galaxies. The cosmic microwave background will fade beyond detectability. The evidence of expansion, of the Big Bang, of cosmic structure, will be erased by the deepening event horizon. Their universe will appear static, small, and isolated. They will not know what once existed beyond their cosmic island. They will not see what we see. The cosmic boundary paradox will shape not only the limits of knowledge today, but the limits of knowledge across all of cosmic time. It is remarkable, almost poetic, that we live at the moment when the universe is most readable, when the cosmic web is still visible, when galaxies still populate the sky in abundant numbers, when the afterglow of creation still graces our instruments with faint ancient light. We sit in an era of rare transparency, a narrow window where the universe reveals its history. A brief moment when the horizon is large enough to hold the story of cosmic evolution, yet small enough that the story has not faded away. This window will not last forever. There is something quietly emotional about this. The universe does not simply expand, it forgets. The accelerating growth of spacetime erases its own past from future observers. The cosmic web dissolves into darkness. The distant galaxies vanish beyond reach. The universe becomes larger, but the story we can tell becomes smaller. The boundary paradox reminds us that knowledge has a horizon, that exploration has a limit, that seeing the whole universe is impossible not because we lack technology, but because the structure of reality itself forbids it. And yet, this does not diminish the wonder. If anything, it deepens it. The fraction we can see, though small, is breathtaking. It contains billions of galaxies, each with billions of stars, each with histories measured in billions of years. It contains cosmic collisions, starbirths, supernovae, nebulae, and quiet glowing spirals drifting through space. The universe we can see is vast beyond comprehension, and the universe we cannot see is vaster still. This paradox, gentle and immense, is not a contradiction to fear. It is a reminder of our place in a cosmos that is both infinite in possibility and finite in knowability. It teaches us that mystery is not an obstacle, but an essential part of the universe's design. And as we drift toward the closing of this cosmic journey, one final quiet reflection rises at the edge of our understanding.